What's up, guys? It's Utku again, here for another video. Today I'll be doing another fluids problem. It's from my homework, so I was like, might as well. So this problem is from chapter 5, problem 45. The textbook is called The Fundamentals of Fluid Mechanics, 6th edition. It's from them. All right. Determine the magnitude and direction of the anchoring force needed to hold the horizontal elbow and nozzle combination shown in figure P5.45 in place. Atmospheric pressure is 100 kilopascals absolute. The gauge pressure at section 1 is 100 kilopascals. At section 2, the water exits to the atmosphere. All right, so a couple of important things. The first thing I want to go over is the difference between absolute pressure and gauge pressure. I think it's important to know. So gauge pressure is defined to be P absolute minus P ATM, which P ATM is already an absolute. So absolute pressure is vacuum being zero and everything up just being a pressure. So atmosphere having 100 kilopascals in absolute pressure. That's the pressure that we feel every day, around us and everywhere. And gauge pressure is nice because usually atmospheric pressure is not that important. So like if you don't have to start from vacuum being zero, starting at atmosphere being zero is a better option because, which in this case, we get to just call P2 when it's open to the atmosphere to be at zero pressure, but gauge pressure. So we have two options. Our first option is that we take we use gauge pressure throughout this problem so that our P1 then becomes 100 kilopascals. Gauge or pressure 2 becomes 0. Or our second option being P1 is 200 kilopascals. Because we would have to convert from gauge, which is it's 100 kilopascals as a gauge pressure. We'd have to convert to absolute, which would just add the atmospheric pressure in absolute, which is 100 kilopascals. So that would be 200 kilopascals. And then P2 would become 100 kilopascals. I like the first option where we have P2 being 0 because we get to just cancel it. It just goes away. We don't have to deal with it. So I'll be using that gauge pressure. I'll be using gauge pressure from now on. All right. With every question, I like writing what's given to me because then I can see what I have, what I'm missing, and then at least we'll have an idea of what we'll need to do to get what we're missing. So let's see. I'll start with V1 is equal to 2 meters per second. Pressure 1 we said was 100 kilopascals. And our area 1 is equal to pi over 4 times 0.3 meters squared. The 0.3 comes from, I will show you, 7. So we're given 300 millimeters and 160 millimeters for our diameters. So the conversion rate from millimeters to meters is 1 meter is equal to 1,000 millimeters. So you just divide 300 by 1,000, you would get 0.3. That's that. Then let's see, V2, we don't know. P2, we know it to be 0. And A2 will be pi over 4, 0.16 meters squared. Same thing, just converting. Should get 0.0201 meters squared. Perfect. So missing V2 and having both areas tells me usually that I will be using continuity to find the second velocity. Usually you only have a few options. You can find velocity from flow rate, if you're given that, which is very similar to continuity. second option is continuity. And the third option is from the Bernoulli equation, because you have velocity in that equation as well. So I believe those are the only three options that you have to find the second velocity or third velocity that you don't know. But here, because we're not given a flow rate, because we know we're not going to use Bernoulli's. We don't need to. So we're not using that, and the one we're left over with is the continuity equation, which is rho VA is equal to rho VA. Obviously, these are 2. I mean, this is 1. So rho V1A1 is equal to rho V2A2. In this case, we're going to because it's the same fluid all throughout, our density is the same, so they just cancel. So we're just left with V1A1 is equal to V2A2. V2 will equal the ratio between the two areas, A1 over A2, multiplied by V1. The nice thing about this is usually, even though we solve for the area, we don't always have to, because I'll show you why after I write this. As you can see, the pi over 4 is cancelled, so then it just becomes a ratio of the diameter squared over diameter squared. So you don't have to find the area. This which will give us, and I just want to make sure, 3.52 meters per second. Oh wait, I forgot to multiply by velocity. I apologize. Not 3.52 times v1, which was 2 meters per second. So then it would be 7. Perfect. Now we can continue with our problem. So this was from the section Reynolds transfer theorem, linear momentum. So that just tells me that I will be using Reynolds transfer theorem, linear momentum. Let's just write that down. This is just the sum of the forces is equal to plus control surface rho v times vita n dA. I'm not sure if it's told that we have steady flow, but I'm going to assume we have steady flow, and that's the case. So then this part goes to 0, and all we're left with is sum of the forces is equal to control surface of rho v vita n dA. Alrighty, so let's set up the equations. So you will need this Reynolds transfer theorem equation for both exits, or as many exits as you have, or sections, I want to call them. Yeah, sections. So the sum of the forces in the x, because we're just looking at x, is x right here, so it's going to be x. What can I, oh, for some reason I can't draw on this. Oh well, but you can see the x right here though. What is the x and y right here? No, I can't draw on it any. Oh, that's right there. I think I did. Yeah, there we go, right there. All right. Some of the forces in the x. So as section 1, we'll have rho. Okay, now we're gonna have velocity. Now let's check where velocity is going in terms of our x direction. So our velocity is going to the right, and we said, or the question said that our x to the right is positive. So that means our first v is going to be positive. Then we're going to look at v dot n. So that's the relative velocity. And that is going to be, we dot it with the normal vector from the control surface. In this case, the control surface is, the normal from the control surface is 180 degrees away, or 180 degrees from V1. So they're opposing each other. And the dot product, the more likely they are, the more positive you get, which is usually 1. And the more apart they are, the more different they are, the more negative you get, which is -1. So if they are parallel, it's a 1. If they are opposing each other, it's -1. In our case, it's the second one, so it's -1. So we'll have a negative with our velocity. And then we have our dA 1 plus our section 2. We're going to have rho. Now let's look at our velocity. Our velocity this time is going opposite our positive x direction. So we'll have a negative velocity for our first velocity. And for our second velocity, v dot n, we can see that they're both facing the same way. So that will be +1, and it will be positive v2 times dA2. Okay, I'm just going to... Perfect. Now let's just get those guys out of the integral. Everything comes out. Rho is constant, v is constant. So you just get an a out of those integrals. So we'll be left with negative rho v1 squared times a1 plus, or not plus, sorry, minus, because there's another negative over there, rho v2 squared a2. And that will be equal to the sum of the forces in the x. Now if I just pull out the negative rho, we're left with v1 squared times a1 plus v2 squared a2. If we plug it in, plug in our values, which we get 1,000 kilograms per meter cubed. That's the density of water, 4 degrees Celsius. And we're just going to assume that that's going to be good enough for this problem. And then usually if you're not told the temperature or density, you're just good to use that 1,000 kilograms per meter cubed. And even if you don't want to use that, I think at 20 degrees Celsius, it's like 998 point something. So it's very close, so you'll be fine. Okay, so now V1 we said was 2 meters per second squared multiplied by area 1, which is 0.0707 meters squared plus 7.03 per second squared times 0.0201 meters squared. And that should give us, let's see what it gives us. Minus 1,000 times 2 squared times 0.707 plus 7.03 squared times 0.0201. That gives us negative 281.8 newtons. All right, and I'm pretty sure that is it. Determine the magnitude and direction of the anchoring force. Yeah. Oh wait, that's not it. No, what am I doing? No. That's just the forces. The force that the water is exerting on the pipe, or that's the force on the water, and then the water is going to exert the opposite of that force. Let's just draw a free body diagram. You'll understand what I'm talking about. Free body diagram. So we go like that, boom, 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 something like that. That's good enough. Alrighty, so we have P1, A1 going in, nothing in P2, which is just 0, and then we have our Fx. Our Fx is negative 281. So this is how I do mine, because it's hard to understand what that negative 281 means on the free body diagram. So the way I think about it is, I said that's the water, that's the forces on the water. That's how I think about it. That's the forces on the water. And the water is going to exert an equal but opposite force on its surroundings. So what that says is the Fx negative would normally go left, but because it's doing the opposite, it's going to put it to the right. So our Fx hold, I'm going to assume is just going to be this. Because we have P1A1 going to the positive, Fx going to the positive, so we have to have something going to the left to block those two. So now, if you say that sum of the forces in the x is going to equal 0, there's no acceleration, it's not moving, then we can just say the sum of the forces in the x, which is 0, is equal to Fx going to the right, plus we got P1A1 minus our Fx hold. And then if we solve for Fx hold, we get that Fx plus P1A1 will equal to our Fx hold. So now if we just plug in our values, I'm just going to take this down here. Boom. So we're going to say, so Fx hold is going to equal Fx, which we said was negative 281.8. But here I will not be putting negative because I already did the flip. Remember, this Fx, the negative one, is of the water, but we don't necessarily care about that. We want the forces on the pipe, on the metal piece. So that force is equal to 281.8, the positive version. So 281.8 newtons plus our P1A1, which we said was 100 kilopascals, times the area, which was 0.0707 meters squared, I believe. Yeah, 0.070. Okay. All right, and that will equal 281.8 plus 100 times 10 to the 3 times 0.0707. Hi guys, it's me, Utku again. Before we get started with the video, after I stopped recording, I went back to my notes and I realized I made a mistake while I was doing it, calculating. When I was doing this calculation on my calculator, and I forgot to put the parentheses on the calculator, so I got a different value than what I should have gotten. I should have gotten, instead of 288, I should have gotten, or 281, it should have been minus 1276.16. And this answer would then change to 1276.16, and this changes then to be 8,346.16, which is, yeah, what should have been. Perfect. Yeah, I apologize for that. All right, back to the video. That gets us 7,351.8 newtons. And that will be our answer. Fx hold. That's what we were asked. And that's going to be the answer. Alrighty, guys. Thank you guys for watching. It was a quick and an easy problem. And I hope you guys were able to understand what I was trying to say. And I'll see you guys on the next one. Take care.